Hello, welcome to the video. In this lesson, we're looking at section 9.3, where we're going to be looking at similar right triangles. So, in the previous chapter, we talked about uh, similar triangles, and the reason why those triangles were similar is because a corresponding angles were congruent and corresponding sides were proportional. Now, in this lesson, we are going to look at right triangles that kind of tie in with the altitude. And when you have an altitude of a triangle with more specifically a right triangle, something happens. And what happens here is when you get that altitude, which means like this point here, point C is a line segment that is 90 degrees from the hypotenuse from the big triangle. What happens is not only you get that large triangle, but it also breaks it up into two smaller triangles inside the big triangle. What happens is because of this theorem, it states that when you have an altitude, the not only is the big triangle similar to I call this like the medium triangle, and this one's the small triangle, and then the larger triangle, we'll call it the large triangle. All of the, of course, those consecutive triangles that are inside there are also similar. So we can say that triangle ABC is similar to the blue triangle CBD, and triangle ABC, the large triangle, is similar to the medium one, triangle ACD, and the medium and small triangles are also similar. So what I also like to do is not only do I tie in calling the triangles the small, medium, and large triangles, I also like to tie in uh, different names for each of the side measurements. So looking at the large triangle, you know, we have AB, which is the hypotenuse. We got that. But we have our two legs. I like to call them by a specific name. All right, so like AC is longer than CB. So I'm going to call this one the long leg, and I'm going to call this one the short leg for this triangle. Now, I am going to look at the medium triangle, the red triangle here on the bottom. You still have your hypotenuse right here, AC, and AD is larger than CD, so this is my long leg here, and this is my small leg here. And then finally, I have my small triangle. My hypotenuse is here for this triangle. This is my long leg, and this is my short leg. So if you notice, um, some triangle names are different than with respect to which triangle I'm looking at. So for instance, for example, if I looked at the large triangle and I was looking at line segment CB, in that triangle, it's considered the short leg, but in the small triangle, it's considered to be the hypotenuse. So you can use those names to help you find any unknowns that they're asking us to solve for. Okay. And then we can write a proportion to help us with those specific findings. So for this one here, they're just asking us to simply identify the similar triangles. Okay. So basically, you're just kind of essentially doing what the theorem did, looking for the large triangle, looking for the medium triangle, and you're looking for the small triangle. So uh, before I write any similarity statements, I am just going to name each triangle. So I got my large triangle, and I'm going to name it triangle RCB. TS, because I like to use the 90-degree angle as my middle value. So could you named it RST? Yeah, yes, you could. But then you'd have to be consistent throughout um, the whole other names with those values. But I just like to leave the middle vertex as my 90-degree angle. So now if I look at the medium sized triangle, in that particular instance, since RT is the long leg in that one, I'm going to say that triangle, it's going to be RUT because RU is my long leg in that particular triangle. And then finally looking at my small triangle, it's going to be triangle. So with respect to the long leg, it's going to be triangle TUS. So all of the reason why I ordered it the way I did was T, U, and um, U were all vertices with the 90-degree angle, and RT and RU and TU were all long legs with their respective triangles. So to write these similarity statements, I'm going to say that first off, triangle RTS is going to be similar to triangle, I'm going to use the medium, RUT. Then I'm going to say that triangle RTS is going to be similar to triangle, so the small one, TUS. And then finally, triangle RUT is similar to triangle TUS. So there's going to be three similarity statements that get written with respect to those triangles. So here it says a roof has a cross section that is a right triangle. The diagram shows the approximate dimensions of this cross section. They want you to find the height H of the roof. Okay, so how you go about solving these different problems, because we have it given the altitude. Since we are given the altitude, we have three similar triangles, which means that we are going to attempt to set up a proportion. Now, the proportion that you're going to use is with respect to the information with the different triangles that you have. So if you notice, the large triangle in here, XYZ, you are given every single dimension. You are given the hypotenuse, you're given the long leg. So here's the hypotenuse, here's the long leg, here's the short leg. You're given all that information. So using that large triangle is going to be very helpful. Now, looking at the small triangle, you're trying to find H, which is the long leg, but you're also given the hypotenuse in this particular triangle. So what I'm going to do is say, okay, I'm going to write this as a proportion of H over 3.1. All right. Now, H with respect to the small triangle is the long leg. And 3.1 with respect to the small triangle is the hypotenuse. So when I set up the proportion, when I look at the large triangle, I need to put long leg and hypotenuse with in that corresponding. I mean, you could have had it flipped for sure, but this is just how I set it up. So looking at the large triangle, my long leg is 5.5. My hypotenuse is 6.3. Okay, so I was consistent throughout my whole fraction. Long leg was on the numerator and hypotenuse was on the denominator. So now I can go about using cross product. So this is now going to be 6.3 H is equal to 3.1 times 5.5, which gets you 17.05. Dividing everything by 6.3, I get a value for H that is about 2.7, yeah, 2.7 meters. And there are other ways that you could have possibly solved this, but this was the way that I went about solving it. All right, so again here they want us to find the value of x. So if I look at, let's say I look at number 4. All right, if you like help on 3, please leave a comment. I'm more than happy to go about solving, but they look like relatively similar problems. So looking at number 4, looking at the large triangle, they give me all the measurements. They give me the hypotenuse, they give me the long leg, they give me the short leg. So I can look at the medium or small triangle to go about in solving this. So let's go with the medium triangle. So the medium triangle, they give us, looks like the short leg for the medium triangle, and they give us the hypotenuse for the medium triangle. So I'm going to write this in as x over 12 is going to be proportional to, so now remember x is the short leg and the hypotenuse is 12. So that means when I'm looking with respect to the large triangle, I'm looking for the short leg of the large triangle and the hypotenuse, all right, and keeping things consistent in my fractions. So looking at that, my hypotenuse in this case is 13. My short leg with respect to the large triangle is 5. So now I can go 13x is equal to 12 times 5, which is 60. Okay, so here then I can just divide 13 from both sides. So 13, or I'm sorry, 60 divided by 13 gets us a value roughly 4.62. All right, if you wanted to leave it as a fraction of 60 over 13, that's fine, but that is about what that value of x is. So looking at geometric mean, geometric mean is going to be useful when it comes to solving unknowns for these similar right triangles, because you may be given an unknown and you may be only given 2 other values, but your hopes is that those unknowns for x are able to write into the cross product, so you can write in it as x squared. So essentially, the geometric mean, if you're given 2 values, it is just going to be the square root of the product of those 2 values. So for instance, if they ever ask you, all right, I want to find the geometric mean of 24 and 48. So what you're going to do is you're just going to take the square root of 24 times 48. All right, so 24 times 48 is 1052. If I were to attempt to take the square root of 1052, it is not a perfect square number. So what we're going to do is we need to write this out as the product of these 2 values where one of them is a perfect square number. So so if I took 1152 and divided by, okay, so I know that 576 is a perfect square number, and if I multiplied it by 2, I'd get 1152. If I took the square root of 52, or took the square root of 576, I'm sorry, I would get 24. So then my result is going to be 24 times it by the square root of 2. Anytime they're looking for a geometric mean, they're usually looking for the exact answer, unless they specifically say I want the approximate answer rounded to the nearest 10th or 100th or whatever it is. But they're mostly looking for an exact answer, and usually the exact answer has some form of radical if it is not a perfect square number inside um, the square root. So these are theorems with respect to the geometric mean. They're useful, yes, but in my personal opinion, I just like to use the short leg, long leg, hypotenuse proportion setup because it's consistent throughout, the entire section in order for us to solve problems. So like I said, in this particular one, like for example A, for instance, you have a variable X, but they only give you two pieces of information. They tell you that the distance from here to here is 6 and the distance from here to here is 3. So you are essentially going to be using the medium triangle, like this medium triangle here, and you're going to be using the small triangle to help you solve for X or find the value for X. So for instance, looking at this with respect to the small triangle X is your long leg and 3 is your short leg. If you were to look at it with respect to the medium-sized triangle, 6 is your long leg and X is your short leg. So if we're going to set this up, so first let's look at it with respect to the medium triangle. So I'm going to put short leg on top, which is X, divided by long leg on the bottom, which is 6. And that's going to be proportional to, so short leg is 3 with respect to the small triangle, divided by long leg, which is X. So if you notice that the two X values, one's on the top and one's on the bottom, that allows us to use that geometric mean formula. So it's going to be X squared is going to be equal to 6 times 3, which is 18. Okay, so then to find X, you just take the square root of both sides. So then X is going to be equal to wherever the square root of 18 is. I'm okay with approximations in this one. So this one's about 4.24. All right, again, last one here, we'll look at B. With this one, same idea, only given two pieces of information, but looks like we can use the short leg here, and it looks like we can also use the short triangle, the small triangle and the large triangle. My apologies. All right, so looking at the different values with respect to the small triangle, y is the hypotenuse in the small triangle, and 2 is the short leg. Now, looking at the large triangle, this right here is your hypotenuse for the large triangle, 2 plus 5, which is 7, and your value for y in this case is your short leg. So setting up this proportion is going to be, so if I looked at it with respect to the small triangle, it's going to be y over 2. So hypotenuse I put on the top, I put short leg on the bottom, and it's going to be proportional to, so if I looked at it with the large triangle, hypotenuse for the large triangle is 7, 2 plus 5 is 7, divided by short leg, which is y. Same thing again, the y's are across from each other, so I can square them. Y squared is going to be equal to 2 times 7, which is 14. Take the square root of both sides, so now the square root of 14 is going to be about 3.74. And that is being able to look at similar right triangles. Hope this helps. Until next time.